to presentation. Of course, and first of all, Denis, and I will also thank on our side of SCOR, Henri and Marie-Laure. And I would also like to thank Grégoire Jacquemin, Valentin RJS, Antoine Eranval, Rita Mahatouk, Antoine Doisé, Tiziano Facina for their contribution. And let me just wish you a very interestful, stimulating and insightful meeting and workshop. And now I give the floor to Marie-Laure. Okay, Marie-Laure, you have the floor.
Thank you, Philippe. Sorry, I'm just... So yes, we are very pleased to welcome you on this third workshop that we held at SCOR in the context of this chair of geolearning and climate change that we fund with other partners to the School of Mine in Paris. The aim of today is to present you some advances and progress that has been done in some research topics. Please note that the presenter today are at different stages. So you will see research topics of people that are finishing the thesis, that have already written an article, some that are just starting. I think that's part of the beauty of it. And what I would like to say as well is that because it's funded by different partners, there are some research topics that were presented and proposed by SCOR and steered by Henry and myself, but we also benefit from some research topics that were proposed by the other partners. And I think this is very rich to see the outcome of it. I don't know if you want to add something.
No.
Okay. So maybe, Denis, I'll let you introduce the agenda of today.
Thank you very much, Philippe and Marie-Laure. And good afternoon, or good morning, or good evening to everyone. First of all, thank you very much, Philippe and Marie-Laure and Henri, for organizing this workshop and welcoming us. It's always a pleasure to come here. As they already mentioned, this Geolearning Chair is a research program. Could you switch to the next slide, please? Yes, thank you. It's a research program which is sponsored by the SCOR Foundation for Science, of course, but also alongside with 3 other sponsors that already have been presented, Andra, BNP Paribas, and CCR. And here you have a picture of the 2 teams. This chair joins 2 research teams. On the one hand, the Center for Statistics and Images at Mines Paris. This is a new center that has been created very recently as of January 1st this year. And that's on the one hand. And on the other hand, a research team from the Biostatistics and Spatial Processes Research Unit at INRAE, which is the French National Research Institute on Agriculture, Food and Environment. The next slide, please. The research domains covered by the Geolearning Chair. We have animation here, so thank you. So this research domain is organized as a tripod with 3 legs in a way. We have geostatistics to handle spatial temporal data, extreme events, and machine learning. And our applications relate to the climate transition and climate risks. So for this workshop, we have selected 5 presentations that will be given by PhD students or postdoc students, and as Marie-Laure mentioned, at very different stages of their work. These students are all funded by the Geolearning Chair and then hence by the SCOR Foundation along with the 3 other sponsors. The first presenter will be Grégoire Jacquemin. He's finishing his PhD right now. He will show us how we can project the return period of some compound events in future climate using a new mathematical approach developed during his PhD. Then Antoine Eranval will present a novel approach to analyze the dynamics of extreme events using the theory of point processes. As a third speaker, Rita Matuk will then present a new mathematical framework for the analysis of extreme events on graphs with application to river networks, I think. And then Antoine Doisé will present a new way of modeling rainfall occurrences with the long periods of droughts, which is of major importance for many risks, including agriculture. And then finally, Tiziano Fassina, he should have presented his first findings regarding the simulation of extreme events using generative AI. Unfortunately, Tiziano cannot be with us today for health reasons. And one of his advisors, Thomas Romary, will make the presentation on his behalf. This selection is, I think, representative of the type of research that we pursue here within the Geolearning chair. And we hope you will enjoy this very interesting session. Thank you.
Okay, is it working? So everyone can hear me and see my screen? It's good. Okay. So my name is Grégoire Jacquemin, and as Denis and Marie-Laure introduced me, so I'm a PhD student, so I'm in my final year of PhD. I'm expecting to defend my thesis in a few months. And I will be talking about the quantification of compound events evolution under climate change through multivariate bias correction methods. So this is a joint work with Mathieu Vrac from the LSEU, Denis Allard from INRAE, Xavier Frelon from Mines Paris, and Valentin Arjaïes, which did an internship under our supervision, which is from ENSTA Paris. So first, I will give some context and present the compound events I've been working on. Then I will talk about modeling those compound events and the articles that resulted from our work. I will briefly present the data and the method of bias correction. And then I will motivate the bias correction of compound events, and I will make some comparison between different methods to do so. Then I will present an extension of our methodology to Europe, and then I will provide some conclusion and perspectives. So first, some context about our study. The key idea is to understand how would compound events evolve in the future under some climate change. Will there be more of them, less of them? Will they be different, and so on? So to do so, the first step is to model some compound events. To do that, we consider some reference data. In our case, it will be some Error 5 reanalysis data. And we'll try to develop some methodology to model those compound events, or we'll compare our newly developed modeling approach to existing modeling approaches. In the second time, the idea is to capitalize on climate simulations to understand the evolution of those compound events. But as we'll see, those climate simulations are often biased, statistically biased, and they require some bias correction, statistical bias correction. We're talking about statistical post-processing of data in order to correct the statistical basis of the climate simulations. So we learn our bias correction between the reference data and the raw climate simulations, and we can apply this correction to past climate simulation in order for us to improve the realism of compound events. So it will be the first axis of of the bias correction presentation. Do bias correction methods improve the realism of compound events? And in a second time, we can apply this bias correction to future climates. And the key question there is, do bias correction methods preserve climate change signal seen in raw climate simulations? Indeed, climate simulation may simulate an evolution of the climate and the extreme events. And the idea is this evolution kept by bias correction methods? It's not something we want to correct or to modify. Okay. So during my work, I focused on two compound events that were used as examples for the methodology and the study developed. So the first one is the Seine-Loire event, which happened in France in June 2016. So this is defined as a spatially compound event. So the idea is that some huge floods happened on the Seine and the Loire River in France in June 2016, roughly at the same time. So these floods were caused by accumulation of precipitation over several days. And to model that, we use the antecedent precipitation index, or API, which is defined there. You have the formula. But basically, it's the sum of precipitation of the preceding days with K, which is a factor of evacuation. You can see it as the evacuation of the water by the watershed. So we sum the precipitation over several days, but we evacuate a bit of water every day. So there, your precipitation is the daily precipitation. We have some parameters for K and N. And so daily precipitation are averaged over the Seine and the Loire watershed. So the Seine watershed is in red on the graph on the right, and the Loire watershed is in blue on the right, for the months of May and June between 1992 and 2021. So we are using first time error 5 data as our analysis on the 1 degree to 1 degree grid. This is represented on the right. The second event of interest in our study is the R event, which happened between Belgium and Germany in July 2021. This is a preconditioned compound event. So what happened, there was some extremely heavy precipitation for over 24 to 36 hours after some moderate precipitation for the previous days, which led to a massive flood of the R River in July 2021. So to model this event as a precondition event, so there's a precondition is that the soil was already saturated in water before the heavy precipitation. So we'll be using the daily precipitation on the day and the API also on the day. The API there is used as a proxy for the soil moisture. So high value of API means a high value of soil moisture, and this is the case for this event. So as in the previous event, the daily precipitation are averaged over the area shown on the right for the months of June, July, and August between 1992 and 2021. Okay, so now that we have given some context, my PhD has been decomposed in two articles. So first part, as I explained, about modeling of compound events. So that's what I will be talking about. It resulted in one article that has been published a few weeks ago. And the second part, which is still in construction article, about the bias correction that I will be talking after. So first, to model some compound events, so for example, the two that I just presented, we have two variables, two time series. We first need to model each variable separately with a univariate statistical modeling that will give a good representation of the extreme. So one classical way to do that is to use a generalized Pareto distribution, or GPD, in a peak threshold context to model the exceedances of a variable above a defined threshold. So this is some classic extreme value theory. In the approach we developed, we will need, however, to model the the whole distribution of our variable, not only the exceedances above a threshold. So therefore, we'll use the extended generalized Pareto distribution, or EGPD, which has been proposed by Navo et al. In 2016, which allows for a complete modeling of the distribution. So we have the easiest shape of the EGPD there. So it's just a GPD to the power of a kappa, with a positive kappa. And G is a GPD cumulative distribution function. So the advantages of the EGPD is that we don't have to select the threshold. The tail of the distribution behaves like a GPD, and the bulk of the distribution is also modeled. There also exist some other forms for F that are a bit more complex, but we use one, but it's not really important for the presentation. So we have our univariate modeling with the EGPD, and we have our tails that behave like GPD. And now we get into the bivariate modeling. So once we have our marginals, we need the bivariate modeling. And to that, we'll rely on a bivariate generalized Pareto distribution. First step, with the EGPD, we can transform our margins to exponential distributions. So this is a technical step that we can do it fairly easily. Then for the bivariate modeling, we need thresholds. So we define two thresholds that are the orange lines on the graph on the right, which correspond to 95th quantile of each distribution. We remove the points that are below both thresholds. So in the bottom left of the figure, we removed the points. We will not be using them. And for each remaining point, we compute a couple E delta. We construct it as it is shown on the graph. So for example, for the red point here, the maximum of its coordinates from the threshold is E, and the delta is constructed orthogonally from E from the bisectrice of our quadrants. And so for each point, we get a couple E delta, so we get two variables. And we showed in our article that the bivariate exceedance probability of any point above both thresholds can be numerically computed from these two variables, E and delta. I won't get into more details in this presentation, but if you're interested, an article about this methodology has just been published in Environmetrics, as you can see on the right. So the key idea is that this BGPD approach, as we named it, so it's formally defined and constructed more mathematical consideration in the article that I just presented here. So it is compared over simulated data to a more classical approach, the copula approach. And we show that in the context of asymptotic dependence, the BGPD approach is more accurate and show less variance than the copula approach. Then at the end of the article, the BGPD approach is applied to the two component events that I just presented earlier. And so this article is freely accessible on Environmetrics. So just briefly presented to you how we can model our component events. And now we'll get interested in this bias correction section I've been talking about. So to do that, we'll use climate simulations. So we'll only consider the SSP 585 scenario from the climate simulation. So this is the most negative scenario with the most radiative carbon emissions. We'll decompose the period 1992 to 2100 into a 30-year period. We'll be working on such a period in order to consider the climate stationary within this 30-year period. We select 10 climate simulations that are named there. We consider only one run for each climate simulation. And we compare 4 bias correction methods. So first bias correction method is no correction. So we're not correcting our data. Maybe it worked, we don't know. Then we have CDFT, which is a univariate bias correction method. And we have 2 multivariate bias correction methods, DOTC and R2D2. Those bias correction methods are compared with 2 statistics, so the bivariate return period T and the coefficient of extremal dependence K, which is a measure of the dependence between our two variables in the extreme. So a few words about the bias correction methods used in the next slides. So the univariate bias correction method is a CDFT, so CDF for cumulative distribution function and T for transform. So we are transforming some CDF. So first, we learn the transformation between the CDF of our reference data, HURA5, and the CDF of our simulation over the same period. So this is a past period, the reference period. We learn this transformation to transform a CDF into one another. We also learn the transformation between a CDF of the simulation over the past and the CDF of the simulation over the future. So we learn how the CDF is transformed by the time between one past period and one future period. And the composition of these two transformations permits to construct the CDF of the corrected simulation over the future. So we just learn how this transform and we can have the corrected simulation over the future period. So this is basically the idea of CDFT. It works very well in univariate in one dimension. There are a lot of articles using it. But the idea is that we're working in a compound event framework with two variables, and there's one aspect that CDFT is not correcting, which is the dependence between the two variables. Therefore, we may need the use of multivariate bias correction method to correct this dependence, and we'll be using and comparing two of this method in a bivariate context. So first, R2D2, we come from rank resampling. So we first need to apply some univariate bias correction, so in our case it will be CDFT, on each variable separately. And then to correct the dependence structure, we have to select one variable as a pivot, which is will be the reference for the rank analogy. We need a reference from the temporary evolution. So we select one of the two variables. And in the rank space, we'll associate points from the simulated data to the reference data with respect to the pivot. So a bit complex to imagine, but we are just modifying the temporal evolution of one variable with respect to the reference. And then we can just replace the simulated values by the one corresponding to the rank of the analogs. So we are manually reconstructing the dependence by respecting the temporal evolution of our reference with respect to one variable selected as a pivot. Okay. The other bivariate bias correction method is DOTC for optimal transport in D dimension, but we'll be using it too. So first we learn the multivariate optimal transport between the reference data and the model data over the reference period. We do the same for the model data, simulation data between the reference period and the projection period. And then we can combine the two projections points to correct the projected data. So this is the natural extension of CDFT into multi-dimension. Okay. A quick slide about the external statistics we are using to compare our bias correction methods. So the return period T and the coefficient of external dependence key. So I think most of you are familiar with the return period. So it is defined as the expected waiting time between two exceedances above a return level xt. So we define a return level, a value, a numerical value of our variables, and we have the waiting time between two of such exceedances. So in univariate, it's just the inverse of the probability to be above this return level with n and theta. So n is the number of data periods, so t is in years, and theta is the extremal index that is needed because we have some temporal dependence in our variables, but some technical details that are also present in our article. And so a similar expression, but a bit more complex for the return period in 2 dimensions is available for compound events in the article I just mentioned. Briefly, the coefficient of external dependence key. So as I said, it's a measure of the dependence between our two variables in the extreme. So it's defined as a limit of the probability that one variable is high, knowing that the other is also high. So key is between 0 and 1, and key of 0 shows some asymptotic independence between our variables, and key equal 1 show an asymptotic perfect dependence. So we are somewhere between 0 and 1, and the closer to 1, the stronger is the dependence, and the closer to 0, the weaker is the dependence. So let's get into the result of this study. So the first question is, do bias correction methods improve the realism of compound events? So what I mean by realism of compound events is in terms of the two statistics I just mentioned. So we can compute T and key for compound events over era 5 reference data. We can do the same for all our climate simulations. And the question is, are they close? Are they statistically significantly similar or significantly different? And with bias correction methods, do we improve this statistics? So to do that, we need to use a twofold protocol. So this is known as a sequential twofold protocol here. So we cut our reference period 1992-2021 in two halves. In the first time, the first half is used as calibration, and the second half is used as projection. Then we reverse the two periods. Second one is used as calibration, first one as projection. And then by combining our two projection period, we reconstruct our interval 1992 to 2021 completely corrected. We do that because we don't want to correct data with the data we use to learn the correction. So there we get some results for the R event. In the first panel on the right, we have results for the return periods. So I will break through this graph with you. So in the red dotted line on the middle, it's the era 5 value. So this is the reference value. We would like to be as close as this line as possible. The other two red dotted lines are some confidence interval, 95% confidence intervals that are constructed through Bootstrap. In gray, the symbols indicate the value of one of the 10 climate simulations. So we have 10 symbols for 10 climate simulations. And we have some 95% confidence intervals constructed through Bootstrap. So it's gray, it's without bias correction. And then in orange, you have with CDFT, in blue, DOTC, and in green, R2D2. We also conducted the statistical test to ensure that a value is significantly different from the era 5 value, and it is represented with a star. So if you see a star, it means that it's significantly different from the era 5 value. So it's a statistical tool to appreciate, but we can also see directly something. So if we consider return periods, so we have one which is significantly different from the R5 value because it's below the lower bound of the confidence interval of R5, but we have also two values that are extremely close to the upper bound of the confidence interval. So they are not significantly different for the statistical test, but they are not really close to the R5 value. With our bias correction methods, especially CDFT and DOTC, we get more value closer to the era 5 value and within the bounds of the era 5 confidence intervals, even though for DOTC we have two values that are significantly different from the era 5, but they are visually closer. For R2D2, it's a bit less clear. We have still one value which is extremely high, and four values that are below the lower bound of the confidence interval, and two that are significantly different. But we can see for CDFT and DOTC some improvement from the result without bias correction. For the key value, we see that the era 5 value is at 0, and the confidence interval is just the point 0. Most of the values are also at 0, but we have some of them that are significantly different from 0 and that are above 0. And we see that CDFT is not really correcting them, and DOTC DOTC is not really correcting them also. R2D2 is behaving the best between CDFT and DOTC in terms of key, with only 2 values different from 0. So those results are, sorry, I'm just going back. So those results are a bit complex to interpret and to clarify. So there are, in an article that is under that is just about to be submitted, we are doing the same study with the other event, and overall we see that bias correction methods are indeed necessary, interesting, but they are not perfect in correcting in the same time the return periods and the dependent structure. But they all do better than the raw climate simulations. Now going into our second question, our second topic, which is about projection, and do bias correction methods preserve the climate change signal that can be seen in raw climate simulations? So first, we'll be concerned about we'll see return periods T for 10 climate simulations there. So we have 4 dots. One for the first one is for the reference period 1992-2021, and the red cross is the ERA 5 value, the reference. And the last dot is the period 2071-2100. And so in gray, you have the evolution of the raw climate simulations, and in colors, you have the evolution of our bias correction methods. So what we can see, and this is the most important point, is that there's a great diversity of behavior among the climate simulations. So each climate simulation almost is behaving in its own way. We don't find a clear climate change signal that is shared among all the climate simulations. So for simulations show an increase in return period, 3 show a decrease, and 3 show no significant evolution between our period, our time and the future. And we can see that in around 2/3 of the cases, the sign of the evolution is preserved by the bias correction method. So only the sign, we're not talking about the magnitude of evolution, but just the sign of the evolution is preserved in around 2/3 of the cases. We can do the same for the coefficient of extremal dependence key. So there, CDFT is not represented as it does not modify the dependent structure. So it's really similar to the gray line without correction. So there are, once again, many different patterns of evolution among the climate simulations. We can see, however, that some bias correction may introduce some unexpected variations compared to the raw climate simulation. For example, we can take the example of the RPSL model, where the raw climate simulations show no evolution of the key value, but DOTC and R2D2 are showing some low, but still some evolution. So this is some interesting points that may be specific to this compound events. But no, there are no climate simulations show a significant evolution in terms of dependent structure. So this event may remain asymptotically independent in the future. So the final part of my presentation is the extension to Europe. So this work has been conducted by an intern, Valentin Arjaes, under my supervision and the supervision of my supervisors. And I will be presenting the results that we found. So the idea is to compute T and key on every grid cell over Europe for an event that is similar to the R event. So if you remember the context, the R event is localized on 1 pixel. So we consider actually 9 pixels that we average. But we can do that for every pixel of Europe or the world, but we kept it at Europe for the moment. And we can define an event like the R event. We can consider the precipitation in the API. And for each grid cell, we can compute some return period T and a key. And the idea is to see if we have the similar evolution all over Europe, or if we see some patterns of evolution across Europe. So the study is conducted only with the IPSL climate simulation. So we would like to extend it to other climate simulation, but it's just a question of time to run the algorithm. And we only conducted it with the CDFT bias correction method. So once again, we would like to do it with DOTC and probably R2D2, but we may need a bit more time. So one key point, I won't go too much into detail there, is that different choices can be made to when we want to extend, make the extension in terms of return levels. So which couple of returns level do you consider? It's not that easy, but here we'll just consider return levels from a 100-year return period for ERA 5 data. So just to be a bit clearer, we consider ERA 5 data on our reference period, so 1992 to 2021. And we consider a return period of 100 years for each grid cell. We can deduce some return levels that correspond to this return period, and then we apply those return levels, those numeric value, to the period 2071-2100 with the IPSL data corrected with CDFT, and we can compute a return period, and this will correspond to a today 100-year event similar to the R event. Then we can compute some evolution, which is the logarithm of the ratio of the return periods, and with the return period of the reference, which is 100-year. Okay, this is the results, what we get. So first, on the left, you see the return period for the reference data on the reference period. So without any surprise, it's 100-year everywhere. So we have some aberrant points which are in blue there. It's some optimization problem in the algorithm, but we'll just not consider them for the moment. And in the middle, you see the return periods for the IPSL data corrected by CDFT for the period 2071-2100. And the difference to the yellow is the evolution of the return periods compared to a return period of 100 years. So on the right, you have this evolution, so the logarithm of the ratio. So in red, you have an increase in probability of occurrence because you have a decrease in return period, so you have an increase in the probability of occurrence. And in blue, you have a decrease in the probability of occurrence. So a 100-year event similar to the R event seems to be less likely to happen in the south of Europe, but more likely to happen in the north of Europe. So those are some preliminary results because we only did it with IPSL climate simulation, with one run of this model, with CDFT bias correction, but we can see a pattern of evolution of this compound events in the future. So another topic Valentin worked on is the extension of the Seine-Loire event. So with this is a spatially compound event with some spatial dependence. So to extend it, we did not consider some watersheds. We could do it, but it's a bit more complicated. So we still consider some pixel and the API on each pixel, on each grid cell, sorry. And so to do this extension, we fixed one grid cell, so generally a major European city, so Paris or Prague, for example. And we computed the extremal dependence between the API at this grid cell to the API of all the other grid cells. So for each grid cell, we get a value of key. So this is a dependence between this grid cell and the grid cell of the selected city. And we did that for the reference period and in the future. So if we go to the graphics, the figures, on the top left, we have for the reference period, so now for Paris, so we fixed our API in Paris, and we see the shape of the dependence of the API over Europe. So it's dependent with all north of Europe and Belgium and the west of Germany. But it's low dependence with Germany, south of France, and north of Italy, and we don't have any dependence with Eastern Europe and the south of Europe. But we can see that in the future, still for the IPSL climate simulation, that we have an extension of the dependence all through Germany, Czech Republic, and even to Poland. Sorry. So we have what seems to be an extension of the dependence, a modification of the shape of the dependence between Paris and other regions. We show the same for Prague. We have a clear independence between Prague and France in the present, but we have low and weak but still present dependence between the north of France and Prague in the future.
So in short, if I understand well, the result of your study shows that, or this study with all the caveat, that we, in the future, we expect more, let's say, the 100-year precipitation will be more frequent in the Northern Europe, and the spatial distribution of those precipitation will be more extended, especially as it seems with all the caveat.
It's not really more spatially distributed. It's like the dependence in the extreme will go further spatially. So we can get some dependence between extreme precipitation events between east of Europe and west of Europe. But
I think Simon had a question.
Yes.
Yeah, I mean, no, just not a question. Just one point is that because this is just one model, and we know, for example, that the climate models, they have trouble simulating extratropical storms. They are too horizontal, for example, in Europe. It might be, in some cases, it might be driven. So I don't have too much confidence to that, to tell you the truth. On the shifting, let's say, or the extremal dependence, that it's a bit further to the east.
It's precipitation, it's not wind.
I know, but I mean, I'm not sure if they are able to model that as well.
No, I mean, yeah, but I mean, it's. I think what is interesting here is that we can all this statistical method is to be able to do this kind of things. After he has done it on one model. Yeah. Now we have to look with if you have the same pattern with other model.
Yep.
But I think it's an interesting outcome that we are able to have a broad understanding of how the distribution or how extreme event may move in a climate changing environment. Using climate model as most as we can. Of course, with all the caveats with the climate model itself.
I agree. I'm just saying that we need probably more models, I think, in order to have more confidence. That's
that's preliminary result just for you.
Yeah. Okay, cool. Thanks.
Yeah. Can I add something? So I agree we need more models, that's for sure. And we also need other bias correction methods, because at the moment it's only CDFT, which is univariate. However, and also one precision, it's not precipitation, it's not a daily precipitation, it's an accumulation over several days with a discount factor to account for runoff and evaporation and that kind of stuff. So it's accumulated precipitation, actually.
Yep. Thank you very much. Very interesting question. So as I say, as everyone said, it's just preliminary results, and obviously more models and more bias correction methods should be added to confirm or infirm those results. So finally, some conclusion and perspectives. So I hope I highlighted the necessity to use a bias correction method when projecting the evolution of compound events. To get more into details, so multivariate bias correction methods are required when the dependence is not correctly represented in the climate simulations. Otherwise, if the dependence is correctly represented in your climate simulation, CDFT may be sufficient. So this is what we can see with the R event where in most models this event is represented as asymptotically independent. So CDFT may be sufficient. One key point is that climate simulations show wide variety of evolutions, especially in terms of precipitation or accumulation of precipitation. There is no clear climate change signal. At the European level, for the IPSL model, An event similar to the R event may become more frequent in Northern Europe and less frequent in Southern Europe. And the dependence between extremes events may spatially evolve across Europe due to climate change. So these two last points are extremely conditional. This is just some preliminary results. More climate simulation need to be studied, as I said, and with more methods. So in terms of perspectives, as I just said, we need to confirm those return periods evolution with other climate simulations, confirm the evolution of spatial dependence, and also a similar study has started about hot and dry compound events. So the idea is to apply this methodology to hot and dry compound events across all Europe. And when I have more time, if I continue in research, I will try to continue this topic. Thank you very much for listening, and if you have any question, please ask me.
Any questions to Grégoire on this topic? In the remotely or in the audience? Okay. Jean-Baptiste? No? It seems to be thinking loud. So. Okay.
Maybe just one on the... Yeah, you have so you had one paper that is published.
Yes.
And you have like another one in mind, or?
Yeah. So actually, what I've presented until the extension to Europe is actually doing the. I mean, I have written everything for paper. I'm just reading it again to correct some mistakes, and then there's a revision of my supervisors, and we plan to submit it to a magazine, to a journal, sorry, in next month.
To Gala. To Gala, nous voici. Sorry. So which new paper do you have in mind? Which journal? Do you have in mind?
It's Natural Hazard and Earth System Science, and NHESS.
Yes. Okay. NES. Okay. Okay. Thanks.
Yeah. So it's really in the publishing stage.
The second part is quite. I mean, I like the first part and I know about it, but I think the second part could be quite powerful in just to see the special extent. Even though I agree with Simos that.
The second paper will include the projections in future, but not the spatial aspect, because as we discussed earlier, this requires more work on other models and other bias correction methods. And the spatial extent, that's part of the internship by Valentin. And we don't have the manpower right now to extend it to, as we discussed. So yeah, we hope to have a third paper someday, but it's not, it's not in the pipeline right at currently.
Rita? Here is sorry. Okay, so I misread the order.
Okay, so thank you. I will talk. I'm a postdoctoral researcher at INRAE in Avignon, and I work with Denis Allard, Thomas Opitz, and Edith Gabriel. And I will talk about the dynamics of extreme events using mark point processes. The context of our work is really the context of the Geolearning chair, and the point is to use all the big data coming from climate model, climate observation, and all the model, especially the reanalysis data and use it to have actionable knowledge on extreme events and climate change. And to do that, what we are trying to do and what we are doing is to mix the method coming from point processes, so something more spatial method, and extreme value theory, and really use event-based approach. So what I will present throughout this presentation is really something you have to keep in mind is just not correlation between a variable as Grégoire more introduced, where you are in the point scale and you try to look at the methodological data. Here we are really looking at extreme events, so it's an event representation. And so the objective is to understand and model the spatial and temporal occurrence and co-occurrence of extreme event. And as I said, we really want to have an event representation. And so we are interested in having a good subdivision of geographic space, something that is useful for risk analysis. So don't hesitate to tell us if you think it's useful or not. And that's what we are trying to do anyway. So this is really a general introduction on mark point processes. I won't go into the mathematical detail, but just so that we are talking about the same thing, a mark point process for us is just a collection of discretably observed stochastic events, and each event would be characterized by a point, and the point can be a coordinate time in space or in space-time, and you will have a mark. The mark would be a numerical variable that will describe the event. It can be something really like the duration of the event, it can be the size of the event, or it can be some numerical value describing the intensity or the severity of these events. And below you have some example of point processes used to model extreme climatic events. So really this is not something new, this has been done before in the literature. And so you have some spatial processes. It's useful to study spatial processes like urban heat island or wind farm layout, something that is regular and you can model that with using point processes. You have some temporal processes also. You can use it to model rainfall bursts during storm or seasonal floods. Or you can also have some spatio-temporal model and use spatio-temporal processes, mark point processes, to model, for example, wildfire occurrence. And here you will use the mark representing the burn area or the duration, and you can also model that using point processes. And we also think it could be useful to model, as Grégoire introduced earlier, compound events. So compound extreme events of climate. So here on the right, you have an illustration coming from a paper that give a framework to study compound events. And we also think that mark point process could be used to model those type of events, because you can see the interaction between the temporal events or between spatial events. So really we can think that we can use it to model all extreme compound events. So this is what we want to do. We are not there yet, but this is what we will want to do. So here it's just two key functions on mark point processes, really simple. Here I will present a temporal setting, but it's something that can work in spatial or in spatio-temporal. But just to be simple, it will be the temporal one. Oh, sorry, I was not in the mic. So you have the intensity function, which is just the mean number of events in a time interval that will represent where you have most events or not. So for a seasonal process, you will have something high in summer and maybe low in winter. You have a correlation function, so this is something that will help to measure the correlation between events over time. And you have some theoretical reason that says that if you are below a certain value of 2R, R being the neighboring of your function, and you can see that below it will suggest something regular with inhibition, and above we will suggest some clustering. So just looking at this correlation function, you can see if you have aggregation or dispersion of events. So this is something really useful if you want to characterize the co-occurrence of events or the occurrence of events, and to describe how they work over time. So this is really the two key functions that we want to study in our mark-point process approach in the beginning. And to do that, we need to construct extreme events. So we are really database. So the point is to go from data to extreme events. And to do that, we use resolution reanalysis data coming from Copernicus. So we, from this meteorological data, we will construct our extreme events. And so we'll have data at the scale of individual pixel, the same as Grégoire, with a resolution coming from the degree or the quarter of degree. And we will show the threshold. And then we say that above this threshold, the events are extreme, which is really classical. And then we'll regroup this exceedance of point to construct a big event. And to do that, we'll use connected component analysis. And we have two numerical applications in mind, and we are doing the two. They are both based on ERA5 data from the Copernicus data store. So we have one for precipitation events and more the interaction between precipitation, wind, and CAPE. And this is with the more temporally center approach. So here we'll really use more the temporal mark-point process. And we have also another one for temperature anomalies, but really more temperature extreme. And here we use more a spatially center approach, but in both applications, we really want to apply method from mark-point process to the study of extreme events. So the two applications are really, they are not the same because it's not the same tools, not the same modeling, but the same approach in the broader sense. We are doing both an extreme event representation, and we applied the method coming from mark-point process to study those events. So here it's just, so for the temporary approach, we have three variables. And we have a big database because we use all the data from the ERA5. So the data from 1940 to 2024. To the end of 2024. So we really want to do a study with a lot of, with a broad historical, so to see the correlation in all the distribution. So as we said, we wanted to have a regionalization that is somewhat coherent for what you use in risk analysis. So we decide to use the NUTS level. So the study is in whole Europe. I didn't say it, but it's really a study on whole Europe and on whole mainland Europe. So we decided to use the NUTS level, which in France correspond to the UOL region. We thought it was something relevant for risk analysis because it's not too big and not too small, so you have some interaction inside the nuts. So the definition here are quite simple. For daily precipitation, we take only, it's really something classical in the literature to study extreme events of precipitation. You use only the wet days, and then you use the daily total precipitation. And we said that above the 98th percentile, it's extreme. The three thresholds are actually made so that we have the same number of events in all the variable. So we don't have some one variable which has lots more events than the other. For wind, we use the 99 percentile, and for CAPE, we also use the 99 percentiles. For all variable, we can compute the exceedance as the value above the control threshold. And this is what we will use to construct our extreme events. To do that, as I said, we will go above one threshold at the individual scale, and then you can regroup these events using connected component analysis. So what we do is we have two thresholds, one spatial and one temporal, and we'll say that each exceedance inside the 50-kilometer radius and inside the 3-day windows, they will be regrouped into one event. So we regroup our individual exceedance at each side, each nuts. So inside each region, we will construct an event by saying 2 points inside the 50 kilometer and inside the 3-day windows. They are the same event. So doing that, we can construct extreme events at the scale of the region, and this will be our point process. Those extreme events will be the point that we'll study after. So here below you have the representation of the result on all this period, 1940 to 2024, in two regions, in Aquitaine and PACA. So it's in France both. So here you can see that you don't have the same regime of precipitation and the same regime of wind, which is to be expected because in PACA we don't really have a summer burst of precipitation or summer storm, but in Aquitaine you can have that. And this is something that we see here in the number. Here is just the number of extreme events. Every circle is the duration. And so you have a lot of events because I have 80 years, so I have here for it's above 700 events by variable, so 7 events of precipitation, 7 on wind, and also for Cape. You can see the seasonality of Cape, which is also known and to be expected. And what we want to study is the co-occurrence and interaction between the variable and across the variable. So to do that, we will use what I described earlier, the K function, but the cross K function is between two processes. So you have X and Y, two different processes, and you can define, and we use something that is introduced in the literature. We can define a cross K function for temporal processes, and that will give you the interaction between the two events. So it will quantify whether an event of type Y tend to occur close to an event of time X. And looking at that, you can say if you have some correlation between your two processes, and you can also construct a test that will tell you if you have temporal dependence or dependence. Saying if you have some factors saying that there could be dependence or independence between your two processes. And this is something useful to compare inside the time window R. It's always dependent on R if you have some interaction. And so this is what we are trying to do after. So we do a test of independence. And to do that, we use a Monte Carlo simulation to build an envelope. And if the observed K function is inside the envelope, then we can say that we seems to have independence. Here, the null hypothesis is that the two processes are independent. So in the simulation, we simulate independent processes. And if the observed K function is outside the envelope, that says that we have a signal towards dependence between our two processes. So here in the screen, you have the processes of PACA, and you have the variable severe wind and severe precipitation. So as we can see here, they seems to be really correlated and dependent, and this is something that we find also in the test. But we don't see any dependence between the Cape and severe wind. So it's we do that by season, so it's the warm season here. And this is something that we also saw, that big events of Cape doesn't always occur near a big event of wind. We don't seem to have some correlation or dependence between the two. And this is something that we also find in the result of the test. We can also do the same for... yes, sorry, there is a question.
I have a question. Yes. Just to understand. Especially it's 50 kilometers, these events. So they have to happen, the Cape, for example, or the wind, they need to happen inside these 50 kilometers, or I misunderstood?
It's inside each region, so they need to appear in the PACA region. And then the 50 kilometer threshold is something to regroup inside the region. So really for PACA, it means that it's in all the region because PACA is not very big.
Sorry, what is PACA?
Okay, PACA is one region in France, yes. Which is stands for Provence Alpes Côte d'Azur.
Yes, sorry.
Okay.
So it's basically what is in between Switzerland and the Mediterranean.
Okay, thanks.
South of Switzerland, the French side. broadly speaking. Anyway, Marseille, Nice, French Riviera, but over all the mountain.
Okay. And so these events happened in PACA region, and then we look at if they happen at the same close in terms of days close by.
Yes, sorry, I did not mention. It's 3 days. Here, the time window is 3 days. Yes, 3 days.
Okay, thanks.
Yeah, thank you. And I think here it's inside the region, so they need to appear in the same region. We can do that, and that's this word we'll say after between region. But here I look at 2 processes inside the same region. So it's not inside 50 kilometers, but it's in the same region. And so Provence-Côte d'Azur is not a big region in time of spatial. It's more than 50 kilometers, but it's not really that wide. Okay, and so here we can see the same result, but in Aquitaine. So it's another region of France. Yes, sorry, I was too quick about it. On the west coast. And here you see, and this is something that we also saw here, we seems to be have an interaction between the event of precipitation and the event of wind and Cape, which is also something that we kind of expected, but it's good to see it in the data and to see that our tool seems to find it. It's not a major breakthrough, but this is something reassuring. And what I didn't show here, but what we want to do is to do that also across different regions. So to compare, for example, Aquitaine with PACA and see if we had some dependence. And the point will be to do that for whole Europe and to do a map of dependence. But the results are still running, so I cannot show you the map. I'm sorry, but soon we will have this map. So this result of the test on whole Europe, and 2 by 2, we can say that this region is correlated with this region. And the point is to see the spatial interaction. But I don't have it right now, but this is the next perspective. And then I didn't know if I had time or not, but if I had some time, what we want to also include in this paper, it's Pfizer weather index analysis. So to do the same, here the events are the temporal, it's only 20 years, so I can represent all the events and it's more clear with this representation. And here we'll also try to do the same on the Pfizer weather index and to try to analyze the interaction between the variables for this hazard. And here, maybe just quick, we do the same with the API of Grégoire. We use also the same, not the API of Grégoire, but also the API, and we try to do, is it correlated with Pfizer weather index? And we saw that it is, but radiation is not. So the point of this study is also to do an analysis of all our variables and try to say which is events that will contribute to the Pfizer weather index. So it's also another application just to show you that it can be useful for all type of events and all type of variable. So this is the conclusion. This is an interesting analysis. Keep in mind, it's not just correlation between 2 variables. It's really an event-based representation and correlation between extreme events using point processes, so it's stronger than just correlation between variables. It's not stronger, but a different point of view, and this gives different results. But we have some improvement. What we'd like to do, of course, is to show you the map I mentioned earlier, really to do this analysis on all Europe, and this is something that we'll have soon. Then we can also improve this method by improving the threshold or improving also how we can do a regroup clustering of extreme events. And also we'll have something would be really interesting for us will be to use impact data or severity variable. In 2 ways, we can use that to have the mark, because it could be, this study can be extended to include marks. Here it's just the number of events, But what will be interesting also is to study the intensity of the event. This is something that we can do. And also the impact data will be interesting because we could see some correlation and with meteorological data, with exposition data, and we think that this representation is really interesting in this context of impact and to see the severity of the events in or claim even to see how this could be used. Okay, so thank you very much.
Thank you, Antoine. Any question locally or remotely? This topic is more, who is more the sponsor? Who is the ID? Ouais.
Yeah, I think as far as I remember, it emerged from discussions that we had together.
Ah, okay. Sorry.
You just wanted to say.
It was we had this discussion on a team meeting like 3 years ago or something,
Okay.
and I think Thomas made the proposition, and we found it very interesting. And yeah.
Okay. Sorry, I thought it was more
Correct,
from CCR, but anyway.
Yeah, I think it's a relatively transversal approach and relatively fundamental, so it's maybe not related to very specific problems specifically in one of the sponsors of the chair, but yeah, it's more fundamental
generic.
and overarching. Yeah.
Okay. All right. There's no question. Let's move to this time. I don't want to make a mistake. Rita.
Yeah. T'es sûr? I start? Okay. Okay. So, hi, I'm Rita Matour. I'm second year PhD student. My PhD focuses on extreme events on graphs to study river floods. River floods are rare events, but they can be potentially devastating when they occur. The objective of my PhD is to study the risk of having simultaneous river floods. How? Let's see. River floods are characterized by very high river flow. Here we plot the river flow measured at one station in the Loire watershed in France from October 2010 to July 2011. We can see a peak in winter. This peak corresponds to an extreme event for one variable, and this peak can lead to a flood. Here we plot the river flow measured at several stations in the Loire watershed. So in this example, we are not studying one variable, but we are studying one vector, like many variables. And we can see that these stations experience very high river flow at the same time, which can lead to simultaneous river floods. So, to study simultaneous river floods, first we take river flows at several stations, but not only river flows. We know that river flows are strongly influenced by weather and climatic conditions. So we will also take weather variables at relevant locations. Let's see this example. It's just an example. We have 3 stations. For each station, we have river flow data, and we want to study the weather variable rainfall. So we will take rainfall, but not at each station. We will just select one location, and we know that rainfall in this location has an influence on these 3 stations. So we have 4 variables, 4 columns, and each row corresponds to one observation. We want to study the interaction between these variables when we have an extreme situation. So we want to model the data. But since you are not in a classical statistic, we will just select extreme events. So we will just select the observations when we have an extreme situation. And these selected observations are called multivariate extreme events. What are multivariate extreme events and how we select them? It's extreme events, but since you are studying one vector, we say multivariate. And how we choose them, how we select them, we say we have an extreme event in one observation if at least one variable is an extreme. So if at least one variable exceeds a high threshold. Now we have our extreme events. We want to model them as we do in machine learning. We have data, we model them, we have a model, then we use this model to simulate. So how we will model them? We'll use a model that exists in the literature. It's a model for extreme events, and it's a graphical model. What's a graphical model? It's a way to represent multiple variables and their relationships using a graph. I will not talk about details, but just we should know that this model, like many models, has parameters. So I have to fit a model, like giving data. I will fit a model. I will find the parameters of the model. But what characterizes this model? That's with a graph. And what is a graph? Here, for example, I have 4 variables. So in my graph, I have 4 nodes. And I see edges, like segments, between these nodes. For example, we can see an edge between station 1 and rainfall. That means if at least one variable exceeds a high threshold, we know that station 1 and rainfall are dependent conditionally to other variables. And we should know that each edge corresponds to one parameter. So the higher the parameter, the stronger the dependency. So now what is the goal of our PhD? The goal is we want to develop a model, but not for one watershed, for all France. Let's start with France. We take France, we select many stations. For each station, we have river flow data. Then we select locations. For each location, we have weather variables such as temperature, rainfall, soil wetness, and other. We select extreme events. We model them using a graphical model for extremes. So now we have our model. But why? What we'll do with this model? We'll give this model as inputs weather variables at different locations. And under these climatic conditions, the model will give us as output the most extreme river flow simulations that we can have at different stations. So we will know which rivers are more likely to experience simultaneous river floods. Just we should know that till now, we don't study the causality. Just the model, like we want to explain the interactions between these variables when at least one of them is an extreme. So we know that 2 variables interact together, but we don't know which one has influence on the other one. So now let's apply on real data. As a first study, we focus on the Loire watershed because it's prone to floods and has both significant population and infrastructure risk. We select 18 river stations in the Loire watersheds. For each station, we have river flow data. Then we identify the sub-watershed they belong to. We identify 3 sub-watersheds. For each sub-watershed, we identify the pixels inside it. And for each pixel, we have rainfall data. So we average the precipitation data from the relevant pixels, giving us, for each sub-watershed, 1 rainfall variable. At the end, what we have 18 river flow variables since we have 18 stations, and 3 rainfall variables since we have 3 sub-watersheds. Like we can imagine a data frame, 21 columns since we have 21 variables, and each row corresponds to 1 observation. We have daily data from 1970 to 2024. So we don't want to model all the data. We just want to select the extreme events. How? we standardize each variable marginally, like we will do transformation, so all our variables will have the same distribution. Why? To make the data comparable across locations and between variables. Then we fix a threshold and we select the observations when at least one variable exceeds a high threshold. And then we model them using the graphical model for extremes. Just, we should note that for each threshold, we select extremes. And for these extremes, we fit a model. So each threshold gives us a different model. And as we do in machine learning, we want to verify if our model is valid or not. So for each threshold, we verify the validity of the model. To finally, we select the most suitable threshold to our analysis. How we do the validation? To validate our model, we have several criteria. The first, we check if the number of selected extreme events is reasonable. Okay, so we fix a threshold, and we select the data that are exceeding this threshold. So the higher the threshold, the lesser the data. And if the threshold is too high, we will have too few data. So the model will be unstable. And if the threshold is too low, we will have more data, but we are not sure that these data are really extremes. So we are not sure that the model will be suitable to this kind of data. The second criteria, it's a mathematical one. Without going into mathematical detail, just you should know that this model has a property. And this property says that conditionally to one variable being extreme, a transformed version of remaining variables follows a Gaussian distribution. So we want to verify if we have a Gaussian distribution. How? We compute residuals based on the following Gaussian distribution, and then we use QQplot. I will not enter into details, but just we should know, like I will explain. We see the black points. If the points are aligned with the red diagonal, we say that we have a Gaussian distribution, and that's very good. So the closer the points are to the red diagonal, the better the model. So at the first, we have many cases. Let's start. First, we take a threshold exceeded by 0.5% of data. This gives us 271 extreme events. It's reasonable. But if we see the QQplot, it's clearly unaligned with the red diagonal. So it's clearly not a Gaussian distribution. Then we take another threshold. It's the threshold exceeded by 0.15% of the data, so a higher threshold. And the number of extremes is also reasonable. It's 124. The QQplot is not perfect, but it's better than the first one. And we can say that it's reasonably aligned to the diagonal. Then the third case, we select a threshold very high, too high, exceeded by 0.05% of data, giving us 54 extremes. But we can see that the QQplot looks very good. So now the question, which threshold gives the most reliable model? To select the best threshold, so to select the best model, we need to balance the number of extremes and goodness of fit. So we consider the second model because it provides a good compromise between these two criteria. I know that in the third case, we have a good QQplot, but since the number of extremes is too few, so the model is unstable. So we consider the middle one. Now we select a model. We know it's a model with a graph, so it has a graph. So we want to visualize this graph to do some interpretation. This graph has 89 edges. So we can't plot 89 edges together because it would look like spaghetti. So we visualize it at 3 levels. First, we focus on one single watershed. Like for each sub-watershed, we plot one graph. For each sub-watershed, we select only the stations located in the sub-watershed and the rainfall corresponding to this sub-watershed. Now we have the nodes. Then we take our 89 edges and we only select the edges between these selected variables. And a little reminder, an edge corresponds to conditional dependency. And here, the thickest the edge, the strongest the dependency. The more the red the edge, the strongest the dependency. So we can see I have a red edge between two stations. That means if at least one variable exceeds a high threshold, we know that these two stations are dependent, strongly dependent, conditionally to other variables. So here we can see that in both graphs, we have strong conditional dependency. We have red edges. So that means within the same subwatershed, stations are strongly, very strongly dependent. And we can see that there is a link between the precipitation, the rainfall, and the river flow, but this link is weak or moderate. Then we move to the second level. Here we only plot the nodes, here we plot all the nodes, like we plot the 21 variables, 3 rainfall and 18 stations, but just we select the edges connecting stations across different subwatersheds. So we just want to see if the stations that are not located in the same subwatershed are connected or not. And here we can see that the link exists, but it's weak or moderate. So within the same subwatershed, we have strong dependency. But between subwatersheds, the dependency is weaker. And finally, the final level, we plot 21 variables, but just we select edges involving precipitation across subwatersheds. So we want to see if there is a link between to rainfall or between rainfall and river flow. And we can see that the rainfall between subwatersheds are connected. It's moderate, but they are connected. But the relationship between rainfall and river flow is weak or one moderate. Now, does that mean that rainfall doesn't have an influence in river flow? Not sure, but just maybe we need to add other weather variables. Like for example, we can have one day, we don't have an extreme event of rainfall, but since the soil is so wet, it might cause an extreme event of river flow. So we should add more weather variables and see the interactions between these variables. And then we had the objective with the simulation, the conditional simulation, like given one or more weather variables, we want to simulate other variables. We want to know how other variables will react. And finally, we will increase the number of variables. We will add more stations, more weather variables to cover all France and maybe all Europe. And now I finish with a quote. Not everything that's faced can be changed, but nothing can be changed until it's faced. Thank you.
Thank you very much. Any question in the call, in the team? Simos?
Yeah, it was quite interesting. I wanted just to ask, so there is no much, or there is moderate, you said, link between precipitation and at the end and the river flow, and that how would you plan to add additional variables like the?
I think it's to have the soil moisture or antecedent condition which is missing. If you take only daily data, it's not a very reactive river basin. I think it's more the antecedent condition which we need to. Yeah.
But how would you try to add them? Actually, these I don't know, antecedent conditions, or I mean, is there a plan to add those information?
Like here, we have 3 subwatersheds. For each subwatershed, we select one variable of rainfall, and to add soil wetness, we can do cumulated precipitation, like the sum of the precipitations for 2 months.
Okay. And I see there are a lot of links, and that's why you needed more than 120 events, for example. Otherwise, it would be quite unstable. So if there is any, so this is there any way to reduce Oh, I'm just thinking because what would be how it's possible to either increase the number of events or reduce the connections in order to make the results more stable, because maybe they are too high resolution would be something to consider.
In fact, we have another criteria, but I didn't talk about. But also, we don't want the model to be so complex, so we don't want to have so much edges, so we will have so much parameters. So we are also finding a solution to the algorithm.
Yeah, reduce the edges, so then you could be able to yeah, that could make maybe sense to select stations that are more, I don't know, more important somehow.
Yes. In fact, that's what I did also, because when I selected the stations in the Loire, we had 100 stations, but not all stations has so many data. And these are the stations where we have a lot of data, so we said that are the important stations.
I see.
Yeah, maybe I can add something here. So currently the inference on the edges, so where we put them, it depends on some kind of extremal correlation. And yeah, one of the next steps would be, well, to keep the same model, but to make the edges causal. So there are causal algorithms that allow us to select the edges based on, well, on causal principles. And this could allow us to have less edges that are physically more meaningful and that are stronger. And so that's also one of the next modeling steps.
Makes sense.
Okay. Let's move to the next one. C'est Antoine, yeah.
Yes. So, hello everyone. I'm going to show you my work on modeling daily precipitation occurrence. And one particular issue we are focusing on is the fact that we want to generate scenarios and focus on long periods of drought. I'm a third year PhD student working with Denis Allard, Philippe Navot, and Olivier Vantamberger. Okay. So first, we are going to focus on the purpose of the study, why this issue is of particular significance. In the second part, I'm going to roughly present the rainfall occurrence modeling without focusing too much on the mathematical details, and then focus on the results, and then show the conclusion and the next steps. So just one word about the purpose of the study. So the idea is that droughts and floods and the rainfall occurrence can be linked to many different risks, which can be direct and indirect. And another point is that the whole distribution of the precipitation, the bulk of the distribution, but also the extreme events can have a significant importance in those risks. That's why we want to model that whole distribution of the events linked to rainfall occurrence. The data we are going to focus on are European data in order to, we want to be able to model precipitation occurrence on a wide range of data and a wide range of rainfall dynamics. And we are trying to keep, be very close to the raw data and don't process them too much. So just one slide to focus on the fact that in Europe, you can have stations where you have like a very little period of drought, but in the southern parts, particularly, you can have a very different water rainfall occurrence dynamics. Okay, And just one last word to focus on our workflow. The idea is that we want to be able to generate scenarios for risk assessments, and there are two ways to do that. The first one is just use recorded data, but we have several major limitations. The first one is that you can generate long scenarios. You are limited to the recorded duration. You have just one run of data, so you don't catch the internal variability of the climate. The major issue is that you can extrapolate beyond recorded values, and that's something we would like to be able to do, is that we want to be able to extrapolate in the tails of the distribution and have an idea of the risks of very extreme events. Those issues can be solved using stochastic weather generators, which goes through modeling the process and then be able to generate from this model. And when you do that, you don't have any limitation in scenario length. And if the modeling is correct, lets you do this, you can eventually extrapolate beyond recorded values. So that's something quite important when to focus on. Just a word about what we are focusing on and how to express it mathematically. So Rn is a rainfall occurrence indicator. So we are looking at our data is rainfall occurrence at different stations. And something we are focusing on is the duration of those rainfall spells or the drought spells, which we are going to denote tau. This is just something to focus on the issue we want to tackle. So we are going to compare two things. The first one is the empirical survival function. So we are going to look at the tail of the distribution of rainfall occurrence and, in that case, drought occurrence. On the left-hand part, you have the empirical survival functions. That function is very close to the raw data. And on the right-hand part is a very classical modeling, which is a geometric distribution for rainfall duration and drought duration. And why is this of importance? Most rainfall stochastic weather generators and rainfall occurrence generators are relying on a Markov modeling, a simple Markov modeling, which is strictly equivalent to having geometric duration, geometric spells. So we want to focus on to compare raw data on that modeling. And what you see on that slide is in blue the very raw survival function, so something close to the data. And in red, you can see the modeling with simple Markov models, so geometric durations. What you can see is that you have a good fit in the bulk of the distribution, but when you are looking at the tail of the distribution, so the right-hand part of that graphic, you can see that you have a gap between empirical values and the simple Markov modeling. And what's something we want to focus on is being able to fill that gap. Okay, so now how do we want to avoid that issue? That very slide, you can see the idea between our modeling. So at the left part, you can see a toy data example in which you have like 3 days of rainfall occurrence. So the first, the second, and the 6th day. And you have a sequence of 3 days of dry spells. On the right part, you can see two kinds of modeling. So on the upper part, what you see is the classic simple Markov modeling, in which you model rainfall occurrence by one state. It rains or it doesn't rain. When you do that, what you have on the just below the first modeling is the geometric distribution of spell distribution. So the idea is that when you have a simple Markov modeling, what you will get is geometric duration when you are in a geometric distributed wet spells and dry spells. And we saw that leads to a problem in the tail of the distribution. So our idea is to enlarge the Markov model and have a Markov model in which in each state you know that you are, if you are in a if there are rainfall, so rainfall occurrence, but also another information, which is the duration of the current spell. So you just add some information. And when just mathematically you express the distribution of the spell durations, what you see is that we have a much wider set of distributions that you can get. And if you do the math, what you can see with a very simple theorem is that you have a one-to-one correspondence between choosing a spell distribution or choosing the model we just looked at in the previous slide. So the idea is that with that kind of modeling, we can have whatever spell distributions that we want. So that's kind of something convenient to work with, to have some model which is flexible. It's just in that slide you just have like some example of link between our modeling and different spell distribution. And that's just a slide to give the mathematical details of a model. The model we just described, in which you can choose the spell length distribution, in which you can choose that spell length distribution. So the idea is that with that kind of modeling, we just have to choose a spell length distribution, the one which matches the more the data, and then we can retrieve the Markov model which gives that kind of spell length distribution. Okay, so just to finish the modeling, we are going to detail what kind of distribution we want for the dry spells and the wet spells. The idea of the dry spell distribution, we will use an extended GPT distribution, which is a little bit modified. So it's the distribution Grégoire talked about in his presentation. That distribution is convenient because it lets you control the bulk of a distribution, but also the tail of a distribution with the classical psi parameter, which tells you how heavy is the tail of the distribution. For the wet spell distribution, we are going to use something quite classic, which is a mixture of two geometric distributions. And that way, we have detailed the whole structure of our modeling. So now we are going to show some results with this modeling. First, we are going to look at the bulk of the distribution. So we have histograms in which we compare the raw data in black. And, in orange, you can see the real data histogram. And in black, our modeling. It's in one city for different seasons. And you have like that kind of results for the whole set of stations. So in the bulk of the distribution, we have quite a good match between dry spells and fitted dry spells and real dry spells, which is the same for wet spells. But one thing we want to focus on is look at the extreme values and compare the ones of our model and the one we had in the different stations. So for this, we are going to focus on quantile plots, on which we can compare on the x-axis real durations and compare it to simulated durations on the y x-axis, real duration, and the y-axis we have simulated durations. So we can see that simulated dry spell durations we have a quite a good match between both. On the same station for different seasons, and we have something quite similar in the whole set of stations. And that's the same for wet spells durations. I show again this graph, which was the first one which motivated our study. So here we are in a station in Aktopol, which is in Bulgaria, in which you have like heavy, very severe long dry spells. And what we saw is that we had a gap between the geometric fits and the real data. And in orange, what you can see is that we have a quite better match in the tail of the distribution and still have a good match, a good fit of the distribution in the bulk of the distribution. So that's quite convenient in order to model the whole distribution of dry spell duration. That's just one very last graph. I won't focus too much on the mathematical details, but what we want to focus on is the fact that we want to focus on the likelihood, how likely is a spell to end after a given number of spells. So it's the same thing than earlier. We are going to focus on two different quantities. The first one is a quantity which is the empirical likelihood of leaving a spell after a given number of days. And the other one is the one we get from our model. This gives that kind of graph. So what you have is for two different stations and for the different seasons, what you are looking at is the likelihood of leaving a given spell after a given number of days. And in blue, you have the raw data. And in orange, you have what you get from our modeling. And something that's quite interesting is that we catch with our modeling is that what you can see is for many different seasons or cities, you have a decreasing of the value of the blue dots in the first days. What does that mean? It means that during a dry spell, the longer you stay in that dry spell, the less likely you are to exit that dry spell. So that phenomenon is called persistence in some of the literature. And you see that in our model, we can catch that persistence. And what's something that's interesting is that with our model, we can catch that persistence. And with the most used Markov models, classic Markov models, we can see the literature, you couldn't catch that persistence because you would have like a constant exit probability. Which wouldn't be able to catch that persistence. So that's something that kind of validates our approach, especially to capture the persistence of dry spells. Another result that's kind of nice is looking at the distribution of the Xi fitted in Europe. So the parameter of the distribution which catches the heaviness of dry spell duration distribution. And what you can see is that you have a spatial structure in the south of Europe. You have you are more likely to meet heavy tails, dry spell durations. Okay, so a word about conclusion on next steps. We have a flexible rainfall occurrence model, which is able to model rainfall occurrence and dry spell occurrence in a quite flexible way, and to model the whole stations and seasons in Europe. You have a very fine control on the dry spell tail distribution. So we model much easier heavy tails than classic Markov models, and we have a good persistence modeling. One thing we want to work on in the next months is to spatialize that model. The idea is that we have a Markov model which are able to model at each stations the rainfall occurrence, and we have a very straightforward. The fact that we have a Markov model lets us spatialize it in a quite straightforward way using a copular approach. And another step will be to model rainfall intensity, and to have a way to model it side by side and then spatialize it. So thank you, and happy to hear your questions if you have some.
Hi, I'm quite interested on the specialization actually. So would it be possible to add any predictors like longitude and latitude in order to the specialization? So then create a hazard map of the dry spells, for example? Or why going for a copular?
Sorry, could you? I didn't get the beginning. So we want to add predictors like other covariables. Is that right?
Yeah. If I'm just thinking, if it would be possible in your fitted model, in the dry spell GPD model, for example, to add some covariates like by longitude and latitude, and then fill the gaps in your map, and then in this way create a hazard map. A dry spell I don't know, because in your previous slide you have a map at station level.
I'll answer on behalf of Antoine because I think he's a bit lost. Yeah, the short answer is yes. That's exactly what we plan to do. It's to have maps of those parameters that control the distribution, the spell distribution that Antoine just mentioned. Now, that is not exactly the same as a map of dryness, but we could end up with maps of how likely a drought larger than any given number of days is. That's possible.
Yeah, it would be interesting. Thank you.
But just to be clear, for the moment we use past data. We don't do projection in the future. Okay, these data are the ECAD data, so there are weather station data in the past.
Mm-hmm. Yeah, no, but it would be useful. And then I imagine the models, the GPT model and what was the geometric or I don't remember one for the wet spells. These can be applied anywhere actually. They work well in all these stations.
Yes.
Yeah. Thanks.
Okay. Other question, or shall we move to the last one? There is. Yes, Stefan.
Thanks, Henry. Thanks for the presentation. So how does the model behave with topography, and how does the model behave if you use different time series for calibration?
So for the topography, for now, what we have is a model which works side by side. So we don't have like spatial correlations. So it's difficult to have an idea of how it behaves with topography. What we look at is the dependence with the very simple geographical position. So what you see on that slide. So that's how our model behaves. That's how far we pushed our model on a spatial point of view, but more spatial analysis will come forward. So that was for your first question. And second one is how... Yeah?
Sorry, that's not what I meant.
Okay.
I don't... if you look at the single stations, but at different topographies, like one is in the mountains, one is on the south side, one is on the north side, one is on the west, the east side, one is in the flat area, and so on and so forth. That's what I meant.
Okay, we didn't push that analysis so far. We just looked at what it gave, like in the northern part and the southern part. What we saw is that, like in Sicilia, which is an island, but also in the south, we had like very heavy tailed oxide, but just some like rough analysis of that kind.
Just again to make things clear, what we are looking at here is length of drought in days. Okay. Usually we tend to look at precipitation or heavy precipitation. No, it's duration of drought and in days.
So for how long there is no rain?
For how long there is no rain. And the map here shows the Xi parameter, and the higher the parameter and the more extreme long drought can be. That's what it means. And if the parameter is negative, what it means is that it is upper bounded. The length of a drought is upper bounded. And this is typical of Ireland, I guess.
Well, I don't know if there is a vocabulary, a word for drought in.
Yes.
They don't know what means dry, from a weather perspective or a beer perspective. Ismail?
Yeah, thanks for the presentation. Very interesting. So first question, you are talking about number of days, basically this plot without rain, and the opposite as well. So number of days with rain. And I see you have some points, you talk about Europe, but I see there are some points outside of Europe as well, in Maghreb. I see Algeria, Morocco. My first question is, this is based on